and also diffusion of molecules in the cell, we saw that in some systems we have this idea originated from Jean-Philippe Bouchot, where you have these systems with traps and you have these power law waiting times, and these power law waiting times were so wide that the mean waiting time was, or Sargentine was infinite, and this led to some ergodicity breaking, and we could characterize the ergodicity in these type of systems using stochastic tools. In parallel to this advance in physics, or even before this advance in physics, there is a long theory and a long history in mathematics, and today the talk will be somewhat inspired by mathematicians. This is the first time ever this happened to me, but it's true. So in mathematics there is a subfield of ergodic theory called infinite ergodic theory, which deals with non-normalized distributions in some sense, and I'm going to introduce them, and I'm going to show the connections. In some sense, the two talks are the same, but even if you don't remember the previous one, then forget about it. Now, the way I started looking at these infinite invariant measures was already in 2009. At the time, people were looking at the, as all of you know, there are many systems which are chaotic. The Lyapunov exponent is finite, etc. But it was also known already in 2009 and even before that there are many other systems where separation of trajectories is sub-exponential on average. And people were debating polynomial in some system, or is it stretch exponential, etc. So we were at the time we were interested in this type of sub-exponential separation in a very famous map. It's called the Pomeau Manneville Map. And there was the first time I was introduced personally to these infinite measures. And then I'm going to show you at the beginning this Pomeau Manneville map. And the question will be, can we have in some single particle, at least descriptions, a Boltzmann-Gibbs statistics which is non-normalized? And the answer, of course, will be yes. And that will be the subject of the talk. And this work was done with David Kessler and Erez Agion. It is on the archive, but it was accepted recently to publication in Physical Review Letters. So again, we're going to recap infinite ergodic theory and some deterministic system, recap Boltzmann-Gibbs statistics. Then we'll try to explain what is a non-normalized Boltzmann-Gibbs state. We'll discuss ensemble and time averages, which you can calculate in these systems. So you can generalize the notions of ergodicity even when you have a non-normalized Boltzmann-Gibbs states. All this is done in a single particle description. And finally, I'll end with thermodynamic relations and entropy maximization, showing that you have some new tools on dynamics also for these type of systems. Now, non-normalized states in physics have several applications, like in nonlinear dynamics, in cold atoms and Levy walks, describing rare fluctuations. So, but here I'm just going to show the relation to Boltzmann-Gibbs. But let us start. We start with the Pomeau Manneville map. So this is a simple transformation. Xt plus 1, t is discrete, has some transformation which I call m of xt, and it's in the interval from 0 to 1. This is the transformation. And it has this branch, which we will call later laminar or non-chaotic, and this branch is going to be chaotic. And you have here the usual trajectory, and you see here this is the diagonal, so obviously here this is an unstable fixed point. So particle slowly escapes from this vicinity, and then it goes to the other branch and it comes back. So it will stay around this point for a long time, then it will go back and forward, etc. This is the dynamics of this Pomeau Manneville map. Now, Pomeau and Manneville, they introduced it in the context of intermittency of turbulence. Actually, they introduced a variation of this map, so I'm not going in the full history. Importantly, this unstable fixed point is marginally unstable. It's a very special type of unstable fixed point called indifferent fixed point. And in the vicinity of this unstable fixed point, we have this transformation. When x goes to 0, it's xt plus a. A is bigger than 0, of course, x to the power z. Now, if you can already intuit, z is a nonlinearity parameter, and when z will go to infinity, of course, this means that this factor will be very small in the vicinity of this guy, so you can expect really sluggish behavior when z goes to infinity. On the other hand, if z is going to be 1, this will be linear, and then you'll have a chaotic behavior there. So it's very obvious that, and we will always work with z greater than 1. So it's very obvious that you have a transition from very, very slow dynamics here to chaotic behavior. But what is more, or maybe less well known, that there is a critical value of z, which is z equal 2, where you have a transition in the total behavior of the system. The transition is between many different aspects of this map. One of them is so Fowler waiting times in the vicinity of this point, and when the mean sojourn time in the vicinity of this point will diverge, I'll soon show you what I mean by that, then you have a transition. The transition is between ordinary ergodic theory and what we call infinite ergodic theory. Of course, at this transition, you have non-stationarity, aging, weak ergodicity breaking, whatever you want. When you cross z equal 2, you go from this case. So z greater than 2, you are very sluggish, and then you go into this anomalous dynamics and statistical physics. So let us see this in action. So first of all, what is known for long time, in the vicinity of the unstable fixed point, over here, the trajectory is nearly continuous, so it's very natural to, in the vicinity of this point, to approximate it by a differential equation, which is super simple. dx dt, I'm just transferring xt plus 1 minus xt is this nonlinear function. A again is positive, z is some number greater than 0. Now, the thing to do is you start at some point, you start at some point, let's call it x0, and you ask how long it will take to reach some boundary, a fixed boundary b. And this is very normal in, And you do that, and then you assume that when you inject back in the vicinity of the unstable fixed point, the injection is more or less uniform in that area. And then you have a time to reach from x0 to b, but because x0 is random, because the injection back is more or less uniform in the vicinity, then you can easily get, this is a really easy exercise, to get the distribution, the probability density function of the waiting times in the vicinity of these unstable fixed points, and they go as 1 plus alpha. Now, this power law distribution, as you know, if alpha is less than 1, and this focus will be on alpha less than 1, the mean sojourn time is infinite, and this is controlled in this case by the map, and here you see the transition at z equal 2. So z equal 2, you have the transition and the mean will diverge. So this implies that there is no characteristic time scale, so when you do time averages, then you will not converge, and etc. So let us look at one observable, and this is in the context of a sub-exponential separation of nearby trajectories. So I look here at the log of m, the derivative of m, which is the local expansion, right? And what do you see? This is as a function of time. For some alpha, let's say 0.75, and you see here, this intermittent type of behavior. You have some regions where this function is, roughly 1, then it goes to 0. It goes to 0 each time you are close to the unstable fixed point. This is very obvious. Two particles very close to this unstable fixed point, they escape very, very, very slowly. So, the Lyapunov exponent there is 0. So this is why you get these zeros. These are when the particle is in the vicinity of the unstable fixed point. And then you have this intermittent behavior. When you go to the other part, it goes to some finite value. And you can define a threshold, and then you can say, okay, this is 1, this is 0. And then if you look at the distribution of times in this 0 state, with this threshold, they will follow the power law that I just derived. This is easily to check numerically. This was done a long time ago. Now we want to quantify the separation, so we look at the sum t equals 0 to, let's say, t minus 1, it doesn't matter, t is going to be large anyway, of log of the derivative of the map. Now, if you look at this graph, it's kind of easy to understand what's going on. This is going to be proportional to the number of events that you cross this arbitrary threshold, roughly. So the number of renewals, the number of times you jumped up here, this is what I call number of renewals, and of course this is not rigorous, but you can make it rigorous. And then you can say, okay, how many events do you have that you cross? Because these are no scale, these are power law. It turns out that the number of events typically scales like t to the alpha. Again, alpha is less than 1. A hand-waving argument would be the this number scales like measurement time t over the mean. But the mean doesn't exist. So what is we replace the mean by t times this power law of the PDF, integrate up till t, and then you get this t to the alpha. But of course, this is very easy to get from renewal theory. If you just count the number of renewals, this is well known in Fowler's book. So this means that when you want to look at this measure of separation, you better scale it with t to the alpha. So what I define as a generalization, at the time we defined as a generalization of the Lyapunov exponent is this sum of the log of the derivative of the map divided by t to the alpha. This means sub-exponential separation. This object will fluctuate. Each trajectory will give you a different number, but we can look at its mean. So to look at its mean, we usually what you do, if you have a Lyapunov exponent, how do you calculate? You need the invariant measure of the system, which is usually normalized. And then you can calculate the average in principle. So here I want to introduce the infinite invariant measure, not as the mathematician do, but as I do it as a physicist. Okay, so it's a little bit different. So what I do is the following. I have the density of the system. The density, I mean, it's perfectly normalized. So this object, you integrate over x between 0 and 1, it's 1. I start, let's say, with the uniform initial conditions, but any initial condition with no delta function, more or less, a smooth initial condition, and I look at the density of the particles at time t, and I make t longer and longer. Then I take this function and I multiply this by t1 minus alpha, and I plot it. And this is what I'm going to call a non-normalizable state. Why is it non-normalizable? It's non-normalizable, it's super trivial. You see, this function goes like t1 minus alpha, so the integral over this function is going to be infinity. Here I have integral over this guy is going to give you 1, but alpha is less than 1, so at t going to infinity, this is going to give you infinity. So for me, this is obvious that this function, the area underneath this in the limit of long time has to go to infinity. This function, it turns out, is independent of x. That's not a trivial statement, but you can do it with a simulation. You just simulate. And you will see that in the limit of long time, so here I'm increasing the measurement time. And you see as time goes by, this will go up, up, up. And then you will see this kind of line. This line is this is the infinite density in the long time limit. This line, we can show, and it was shown by a mathematician for this map, it goes like x to the minus 1 over alpha. So because alpha is less than 1, this power law is non-integrable. What does it mean? It means essentially that the particles are coming closer and closer to the unstable fixed point, and they are piling up there. They have this power law here, x to the minus 1 over alpha. This is non-integrable, because this will be, let's say alpha is half, then this is x to the minus 2. It's non-integrable when you integrate from 0. But of course, for any finite time, you have some cutoff. So you have to think about this infinite density as the limit of this thing when it goes to infinity, and then you approach it. And here, again, it's non-integrable on 0, and then in the vicinity of 1, you will have some modulation. So this infinite density, of course, will depend on the details of the map. It's an invariant density, but it's not simply a straight line. It's non-normalizable, so what do we do with this? Well, it's not so difficult to show that if I want to calculate this generalized Lyapunov exponent, again, in the long time limit, and average it over an ensemble of initial conditions, then in the long time limit, I'll get the usual log of the derivative of the map times this infinite density, and here I need to divide by alpha. You'll soon see why I divide here by alpha, but this comes out of the calculation. And what is happening here? Here, first of all, this equation is very similar to the equations you know. Usually alpha is equal 1, and then here you have the invariant density, and then you calculate your observable in the long time limit. That's ergodicity with the invariant density. But what happens here? Here I have a function which is not normalizable, but what happens is that this observable, where it's not normalizable because of the small x behavior, this function, so to say, cures the non-integrability of this function. So while this function blows up as x to the minus 1 over alpha at small x, this guy goes to 0 strong enough, and the integral exists. And then you can calculate with this non-normalized function some observable. So in infinite ergodic theory, you have classes of observable. This is very important. You have classes of observables which are integrable with respect to this non-normalized state, and classes of observables which are non. Actually, also in statistical physics you have it, because if you think about a Boltzmann measure, I can easily find some observable which is not integrable if I want. But in physics, we don't talk about it because these are crazy observables. So again, we have some observable, and this is an example of one observable where you can calculate this average with an infinite non-normalized densities. And in this example, we plot here the generalized Lyapunov exponent. So when z is less than 2, this is the ordinary Lyapunov exponent calculated with an infinite, with the usual normalized invariant density. This was known by Gaspar and Wang, and the way they plotted it is that they say, okay, at z equal 2, you start to become, here the mean diverges, here you have the infinite density theory, here the usual normalized state. And what we see here, if you plotted just the normal Lyapunov exponent, you'll have here something, and then it will go to 0 here. But because I'm dividing by t to the alpha, it converges to something, and this is the theory given by this non-normalized density. And it works well, of course, when you go to big Z, what happens, alpha becomes very small, and the convergence times becomes very big, and we also have a problem of estimating what exactly is the infinite density. But essentially, all this line is the infinite ergodic theory. And you can calculate this separation. It's sub-exponential. Okay, good. Now the question is, where is the physics? This is math. The question is very simple. And I want to ask, is it possible to have this also for a system which is measurable in contact with the thermal heat bath? So let us just recap briefly on Boltzmann-Gibbs statistics. So I consider one particle in one dimension, and I have this particle is coupled to a heat bath. It's doing, let's say, some Langevin dynamic, generalized Langevin, some stochastic dynamics. And in the long time limit, if the potential field V of x is binding, then of course, as you know, the system will relax to thermal equilibrium with a K Boltzmann T, and then you have a normalizing partition function, assuming this integral exists. So it's simply the integral over the V of x. So z is going to be the symbol of the normalization. And what does the ergodic hypothesis say? So it says simply that you have some observable O. O is a function of the path of x of t. And when you integrate it over time, for a long time, divide by t, this will go, the time average will be the ensemble average. And the ensemble average is calculated, of course, with the Boltzmann measure. And of course, also here we consider observables where this integral exists. But again, in physics, usually that is the case. So this is in the nutshell what I say as ergodicity. And again, in experiment, this was in previous example, you have, some simple hook, spring in water. It fluctuates in time, and I can construct distributions of the ensemble. I can do time averages, one particle after the other. I can do ensemble averages if I have an ensemble. And importantly, initial conditions in this equilibrium distribution are obviously wiped out. And we have to ask similar questions for the case where you have infinite ergodic theory. So let us start just as a teaser. Let us consider the following case. I consider here, this is an exercise my student did half an hour in the afternoon, but if you want, you can do also. Let's take a potential, it's just some potential really, in one dimension. That important property of it is that in infinity, it goes to a constant, and this constant I'm going to call 0. In this example, this is the potential, it's written here, but you don't, it has some peak. 2 peaks, so you have 2 minima, and you have some temperature. The simulations are Langevin simulations with fluctuation dissipation. Usual stuff you can have with the memory, doesn't really matter in this discussion. Now, first of all, a usual way of thinking is let us take this potential and cut it at 2 places, like this, and these are reflecting walls. And then you look at the particles, there are n particles inside the system, they reflect. You do the simulation, and you look at the distribution of particles in some long time limit. It will look something like this. So these two minima correspond to those two minima. Trivial. You all know this in high school or undergraduate studies. Now I'm going to do something slightly different. I take the system. Now the system stretches to infinity. I start with particles inside this box. The number of particles is very large. And I come to the system and I look at it in some interval. This is this torch, which is exactly the same size. And I look at this system and I plot the density of particles conditions that they are there. I'm not looking at all particles. Some particles are going to infinity, but a lot of them stay there. And just I plot the normalized density of particles. It's not a probability density. I normalize it by the number of particles inside, and I plot it. And you see it's like this. Again, you have a minima. This is Boltzmann. It's the same thing. If I give you these two pictures, you could not distinguish between them. What does it mean? It means something very simple, that even though, of course, here there is no normalization because the system stretches to infinity, still you have some, let's call it quasi-equilibrium state. It's exactly like Boltzmann, and you cannot distinguish, even though the partition function here will diverge. So if two things look the same, we have to ask under what conditions do these two things lead to are the same. And for this type of potential field, can we define ergodicity? Can we define averages, etc.? And the answer is going to be yes, but of course, because the partition function is diverging, so we need an infinite density even for this type of simple system, and we will show how this works. So what are the systems that in physics have an infinite density, a non-normalized state, or non-normalization in a maybe surprising work? So this is a very old work of Fermi from 1924. Already at that time, it was old, because before Fermi, other people, and also after Fermi, many people looked at this problem. And the problem is very simple. It's the problem of the hydrogen atom. If you take a hydrogen atom and you put it in a heat bath of temperature T, according to statistical physics, the hydrogen atom will break. It does not exist because the partition function of the hydrogen atom diverges. This was known to Fermi from classical considerations. It's because the binding potential of the Coulomb field is not strong enough. So he noticed this in 1924, and then this was exactly after quantum revolution. So one of the first things Fermi does when you have quantum mechanics is say, okay, maybe we can solve this problem. It bothers them. And how will we solve the problem? We will use quantum mechanics. Quantum mechanics was new. So he calculates the probability for a hydrogen atom. This is R, the Rydberg constant, over I squared. R squared is N squared. This is the usual energy levels of the hydrogen atom. And then he says, and this is 1 over the partition function, you see, and then he says in German that C, this diverges, which means the partition function diverges. And it's very easy to understand because exponential of 1 over n squared, and you sum over n to infinity gives you infinity. It's not a converging series. The same thing is with, this is our Earth, this is our atmosphere. So when we teach statistical physics, if you go to statistical physics books and you look, density in the presence of a gravitational field, you'll have a very famous barometric equation, which is the density above Earth decays exponentially with distance. It's a correct formula in practice, but it's very problematic with mgh over kBt. H is the distance from Earth. Why is this problematic? Because if you add the real gravitational field, then you will have no atmosphere. It means that this way, how do you solve it here? You actually say in practice, what does it mean that the field is constant? It means that S is infinite and flat, right? So this is what we teach our students, but of course it's not that I'm worried that hydrogen doesn't exist, etc., but it's very strange how we teach it because actually the partition function blows up. It's not in textbooks, but many people have thought about it. It still worries people. I looked at who cites Fermi? So people looking at unifying gravitational theory with quantum mechanics in black holes. They do calculation. The mass has a spectrum 1 over n squared like in hydrogen atom, but then what is the partition function? They start discussing this problem again. So this is discussed in some literatures until today. So there are many other examples. One of them is the Bouchot trap model, where you have some density of states which is exponential. And this was in my previous talk. So TG is a measure of the distribution of the density of states. Then you have the Boltzmann factor. Here it's a trap, so it's minus the energy. So it's plus here. And then in the low temperature phase of this trap model, the partition function diverges. Another example is the log potential. I'll discuss briefly later. And the general trick in physics is, okay, things like, let's say you have an hydrogen atom, we know it exists. How do we normalize? We make the universe finite. If you put it in a box, energy levels behave nicely, but I much prefer this philosophy that you can still work with non-normalized distribution. So a simple possible experiment where you could measure these things, this is our suggestion, and then we'll go into the theory, is let us take a surface, and here you have a single molecule above the surface, and people measure this thing, so you can think about it as a membrane, and this, above the surface, this is a real experiment, you have this distance between the surface and the particle, and you measure just the distance, this is in nanometers, and what you see, the particle goes, and then oops, it goes up, and all this is in water at temperature T, and of course, the system will stretch practically till infinity, or let's put it this way, the particle will never reach the upper bound up here. So in this case, we will have an infinite ergodic theory that I'm going to discuss now. So let us start with the simplest model, and that's the Langevin equation with one particle and fluctuation dissipation between the friction and the diffusion. So this is the equation. This is white noise. This is the Einstein relation saying that these two guys are related. This ensures that if you have a binding potential, you will relax to thermal equilibrium. And I assume that this is valid here, and this is very reasonable because, this was checked by many experiments. In this case, the Fokker-Planck equation is very simple. It's the derivative, the second derivative, and here you have the potential field. The potential field gives you the force. So as usual, minus the derivative of the potential gives you the force field up here. And we will consider the Leonard-Jones potential. I thought everyone knows what's a Leonard-Jones potential, but maybe not. So Leonard-Jones, this is V of x, something like that. Importantly, it's flat here. It's repulsive close to the 0. That's the wall, and you have some minimum. And later we will also consider logarithmic potential. Now, what is this non-normalized state? So let us consider solutions, which I call like fixed point solutions. The p dt equals 0. So a mathematical solution of the Fokker-Planck equation is this obvious. This is one of the solutions with a constant. Now, what people usually do is, okay, if this potential is binding, great, then this constant is the normalization, fine. Then we know that under certain conditions, system will approach it. But in general, this is a solution whether this is normalized or not. So what I claim is, what if this is not normalized, what people will usually do, in physics at least, will throw this solution away, will consider it as unphysical because this density for any finite t is normalized, so okay, throw it away to the trash, but we like the things in the trash, we take them out. And for large systems, this solution, which is not normalized, cannot be neglected. But the question is, how do you relate the normalized density to this non-normalized state in the long time limit? So the outline is like this. You have in physics, you have different potential fields. So this is the harmonic potential. Here you will relax to thermal equilibrium. Then you have this log potential, log at large x. I'm going to consider later. It's like this. It looks like binding, but it isn't. Then you have these flat potentials. And then you have, let's say, potential like this, like x to the 3 or minus x to the power 2. I will claim later that only for some subclass of potential fields, you get this non-normalized states. Other classes of potential fields, hell breaks loose, it's a different theory. and we will see why. So we consider this Fokker-Planck equation with asymptotically flat potentials, for example, Leonard-Jones. The force field is non-binding. The density close to the minimum potential, of course, decays in time. So you start close to this minimum, and then particles are escaping. Then if you go at small distances relative to 2 dt. dt is the diffusion length scale. At these distances, a solution of the Fokker-Planck equation is t to the minus alpha exponential v of x k Boltzmann t. How do I know? First of all, you can plug it into the Fokker-Planck equation. On the left-hand side, you have a time derivative. The time derivative of this guy gives you t to the minus 1 minus alpha. That's already a correction term. I throw it away. While this guy, of course, when the Fokker-Planck operator is acting on it, as I said already before, gives you 0. So this is a solution. Now we don't know what is alpha. So what is alpha? It's very simple. When the potential is small at large x, because it's going to be flat, then at large distances you have this solution, which is just free diffusion. You have the Gaussian central limit theorem at very large distances. So if I match these two solutions, I get alpha equal half. So this is the correct result. Now, of course, you can say, how do I know this is all hand-waving? But it's true. You can do the eigenfunction expansions, etc., and show that this is the solution. But the solution, at the end of the day, looks very simple. If I match these two solutions and look a long time, I have, for short distance, this potential over k Boltzmann t, and for large distances, x squared over 4 dt. So this is a kind of uniform. I match these two. And then you have this prefactor that is decaying like square root of t because of diffusion. Now, in the long time limit, if I look at this this Gaussian part of the process, x is some finite number, this goes to 1. So for asymptotically flat potentials, and the limits t to infinity, I have some, what I call a generalized partition function. Soon you will see why. Zt times pt of x goes to the usual Boltzmann factor, where zt is square root of t. In the long time, again, this is all valid in the long time limit, independent of the initial conditions. And this is exactly what I showed you in the simple example. In the long time limit, you go to the Boltzmann equilibrium, but you need to think again, what is this prefactor here? It depends on time, t. The good news in physics point of view, in nature, if you have a surface, all forces go to 0 eventually. So all surfaces, when you have a particle above a surface, the surface potential force will go to 0. So this describes a large class of systems, in my opinion. Sorry. So the question is how general it is. I'm not a mathematician, but it's valid only for the log potential and flat potentials, because I can give a counter example. So consider a potential which is minus x squared. So this is inverted parabola. Because the force here is linear, I can solve this. Also here, you have a non-normalized state, but it's not it's out of my game. It's something else. You can find the solution. It looks like this, where x0 is the initial condition, and you have these exponential decays. And then in the limit of t to infinity, if I multiply this solution by e to the power, instead of having a slowly decaying function t to the half, now I have an exponential, I get this solution. So here, the solution depends on the initial condition. Because what happens, you have this inverted parabola. If you start here, most of the particles will go to the right or to the left. While the flat potential, you lose the initial condition. So there's no and this is not Boltzmann-Gibbs. This is something else. It depends on the initial condition. So it's not general, but it's valid for a class of very wide potentials. Now let us start understanding why and where it's valid. The ensemble average, by definition, is given by the observable, the density at time t. This is normalized. This is perfectly fine. Then I want to calculate this ensemble average. What do? I plug in here this approximation, the uniform approximation that I had before. And then I take the long time limit, and then I get this result. This result is, again, very similar to what you have in ordinary statistical mechanics, but also very different. You have the observable times the Boltzmann factor. You need to integrate, and you need to divide by this partition function, the difference. This function is not normalizable. This depends on time. This is valid under certain condition. The condition is, and it's general, I believe, any observable OX where this integral is finite, it works. Now the question is, okay, you have some observables where you get this result for the ensemble average. Are they important observables? And the answer is they are very important from physical point of view. For example, the potential energy is integrable. So if I plug here the potential energy, because the potential energy goes to 0 at large distances, it cures the non-integrability. Average energy you calculate with this formula. Again, there are many other examples I'll show you soon. For example, occupation times, also entropy, virial theorem. I'll soon show you that many of these are related to this integration over non-normalized state. But there are other observables which are not given by this equation. For example, if my observable is x to the power 2, which is the mean square displacement, it is sensitive to the far tail of the distribution, which means that this observable essentially is diffusing. So this is a non-integrable observable. So here we have the classification into two classes of observables. We can say a lot about these non-integrable observables, but I will not do it here. So I will only consider those observables which are integrable. So how do we see this? So it's very simple. You take a Lennard-Jones potential. Again, this is the repulsion of the wall. You have some attraction of the particle, and eventually at large distances, there's no field. Perfectly normal from physical point of view. You look at the particles, you simulate them, and here I'm simulating them at different times, and I increase the measurement time, and then I plot this Boltzmann factor. And you see where you have a minima, you have a maxima. For some temperature, the temperature is roughly 1/4 of this minima of this potential. And you have, as you expect, here there's no particles, here there are many particles, but then it goes to 1. Because potential is 0. So the area underneath this black curve, which is the theory, is infinite. There's no normalization here. And this is the theoretical curve. And what is happening in reality is that you have this spreading of particles, and as time goes by, they approach this curve. So of course, there's always some cutoff, but this cutoff is pushed to the right, like square root of dt. It goes. Now we want to consider time averages. How do we do the time average? It's done very similarly. So a time average is given by integration over time, and it's this overline here. First I consider the time average, and then I also integrate over many initial conditions. So it's the ensemble average of the time average. Later I'll consider the fluctuations of the time average. This is very easy to do because I have the time integration, and then I replace the order of time average and ensemble average, and inside here I have the ensemble average. I already showed you how to calculate the ensemble average with the Boltzmann factor. So the time average is given by 2 times the ensemble average. And again, this is calculated by the non-normalized Boltzmann state. And what is this 2? This is super trivial. This is a doubling effect. It is found because 1/zt goes like t to the minus half. And then when I integrate from 0 to t, I'll get this 2. So the difference from normal statistical physics, in normal statistical physics, you don't have this 2, but otherwise you see here that the time averages and the ensemble averages are totally related. And more generally, I'll show later that the time average over the ensemble average is given, when you average the time average, is given by 1/alpha. So remember, alpha here is half in this example, but we'll have other examples where alpha is not half. So, for example, you take this Lennard-Jones potential, you do simple simulations, you look at the average energy defined by the ensemble, and then at long times, it goes to this 2. This is one example. And here you can estimate how long it will take to approach the asymptotic limit. There are some deviations because apparently in the units I'm working, this is not long enough. But you clearly see that the ratio is going to this prediction. Very easy. Now, we believe that this is general. And then the question is, we did this for Langevin simulation, for Fokker-Planck. We did it for some generalized Langevin equation in some parameter regime. These equilibrium constants are at least we believe they are general. And then the question is, do we have some some general entropy principle. Wait 1 second. Okay. So do we have some principle here, like in usual statistical mechanics, where you can relate this also to concepts like entropy, etc. And we found out one way to formulate this. And this is done basically on the usual constraints applied to statistical physics with one additional constraint. And the idea is you define a functional of the density, and at first term is the usual entropy, which is commonism, because if I just have this constraint and I take the functional derivative, I'll get all states are equal probability. This is what you do in microcanonical setting. Then you add, because I'm in a canonical setting with a coupled to a thermal heat bath, I add the fact that the average kinetic energy, the average potential energy is some finite number, and I add the Lagrange multiplier, which is beta, which is the usual temperature. I also add normalization, because every Px of t is normalized. So all these three things are perfectly normal. If you take the functional derivative, you get the Boltzmann equilibrium out of this. But what I do here, I added one more, why not? One more Lagrange multiplier, and this Lagrange multiplier is x squared pxt is equal to dt. What does it mean? It means that eventually, because the potential is flat, eventually you have diffusion. Why do I choose x squared and not x4? This is simply because A, I know the answer. Secondly, because this is saying that the central limit theorem, the Gaussian limit theorem, is playing a role here. Because when I'll take the functional derivative here, I'll get, in the long time limit, ptx is this 1 over what I call zt, this potential, x squared over 4 dt. So maybe this is some argument that this holds. Of course, we derived it from the dynamics, but this is an argument, maybe it's more general. And now we can look, for example, we can look at the entropy. And here the entropy is given by this formula. It's given by a formula which is pretty much similar to usual thermodynamics. It's K Boltzmann log of Z. This would be like the free energy over temperature. But now ZT is time dependent. It's like the normalization. Then you have the energy, the average potential energy over temperature. And then because of the new constraint, you have this this new thing, and we can calculate this thing. And what does this say? What is the entropy? Well, the system is expanding. So the entropy is increasing with time. If you had a finite box, entropy would go to a constant. Here it's expanding. So the leading term is trivial. It's like a free particle expanding. You know, you have a Gaussian pocket expanding. So the leading term in long time is log of t with the diffusion constant, etc. And you have other correction terms because of the energy, for example. But these are small at long time. But what we can do is we can, again, look at this entropy as a function of time. And when this blue line is the leading term. At very long times, of course, it's trivial. It's just like a free particle moving. But you can look at the red line is including the correction terms, including the effect of energy. So you see that it converges and it gives you more or less correctly the simulations. So these correction terms are importantly, one referee asked us, okay, please add the following equation. The derivative of S with respect to the potential energy is 1 over the temperature when you fix all the other things. So it's exactly like ordinary statistical physics or thermodynamics in some sense. And okay, this is at least saying that maybe there is something more to this beyond the systems we are looking at. So now but we still have a problem because in usual ergodic theory, the time average converges to the ensemble average. This does not happen here. The time average remains a random variable even in the long time limit. So we are going to define, we need to look at the distribution of these time averages. So we define psi as the time average over the time average mean. So again, this we calculated with a non-normalized Boltzmann distribution. And for example, let us consider the indicator function, 1, 0. This function is 1 when the particle is between some xa and some xb. So the time average of this observable gives you the total time you are in this domain. If you divide it by t, this will give you the occupation time in some domain in space. which in the long time limit will go to the probability if the system is ergodic, right? This is just how long you stay in some region, divide by t. If the process is ergodic, is the probability to be in that domain. So in this observable, you have 1-0 sequences, because you are 1, 0, 1, 0. You are in this domain, then you are out the domain. And again, the particle is doing a Langevin dynamics in this potential. So you have tau in, tau out, tau in, tau out, etc. Usual two-state kind of process. And we know that because the system is infinite, the distribution when you are out of this domain, it will follow a power law distribution. Tau out 1 plus alpha. In particular, for normal diffusion, it's well known that the recurrence times follow alpha equal half, because this is a well-known property of Brownian motion. If you have a flat potential, they return, but the distribution of return times is going to be such that the mean return time is infinite. You always return, you are always recurrent. This is well known from Brownian motion. And alpha is half. So now I give you an interpretation. What is this alpha that I talked about? Now it's a bit more general. Alpha is describing the distribution of return times. Of course, this is very similar to the Pomeau Manneville map, where you add this alpha close to this unstable fixed point. So alpha is the first return exponent, and I assume that you always return, that the process is recurrent, and alpha is equal half. Later we will show other example very briefly where alpha is not half. Alpha is half only when you have these flat potentials. So then, at least for this observable, it's pretty clear that the time average over the ensemble average is the number of times you came into your domain versus the average. And this n is, in renewal theory, well known. This is the number of times you come back. And the reason is that the total time in this interval will be roughly the number of times you return times the average time you are inside, but this n is going to be random. If this alpha, if the return time would be finite, then of course this n will go, by law of large numbers, will go to a delta function around its mean. So the idea is, this is also known, but I just want to give you some motivation. How do we get the PDF of this number of renewals? First we fix n, this is a trick, and we let n be the sum of these tau out. But you see here I'm summing n fixed n now, tau out, they come from a power law distribution. If you sum many random variables and they come from a power law distributed tail, the sum is Levy. This is the central limit theorem of Levy. Now what we do is so if n would be fixed and t random, then this is Levy. Now what we do, so we have the distribution of this variable, and now we switch. We say n is fixed, n is random and t is fixed. And then it's easy and also well known that the PDF of this psi is given by this formula, given by this one-sided Levy distribution. Alpha is between 0 and 1 here, and it's given by this formula. This is called the Mittag-Leffler distribution. It has different names, but you see that the statistics come from Levy statistics because the returns are not so correlated. This is the reason why you have this distribution. And then I can use this. For example, I look at the potential energy in this Lennard-Jones potential as a function of time. And it's a crazy function. It looks something like this. You see these plateaus here are simply when the particle goes far away. So the energy is 0 there. And then you have these crazy events. And then I do the time average. I do the ensemble average. I know how to do it. And I do it for different observables. For the energy, I do it for the occupation time. It doesn't matter. For flat potentials, you will get from this formula, this Levy formula, you get this Gaussian actually. Alpha equal half is this guy. For other alpha, you get other distributions. So when alpha approaches 1, let's say here is, let's say 0.75, then when it's going to 1, you're going to have a delta function here. And that is ergodicity, because then the time average is equal to the ensemble average. So here you have a kind of limit distribution for this time average. In the context of infinite ergodic theory, this is called Aaronson-Darling-Katz theorem. They did it for these, generally speaking, for these maps. It's well known. We just translate it here to Boltzmann-Gibbs statistics. And of course, we can do it also for the first example, for the generalized Lyapunov exponent of the Pomeau Manneville map. You choose the nonlinearity, you have some alpha, let's say 0.75, and you get the same Mittag-Leffler distribution. And this was published again, this was published already 10 years ago. It looks like 100, it's the same. And you have this, again, this Mittag-Leffler distribution, so it looks like it's generic. The difference is that in the new systems you have Boltzmann equilibrium, and here you have some invariant density not related to temperature. It's a mathematical object, but it's very similar. So I'm going to briefly, if I have time, do I have time? Okay, so I'll just briefly discuss the particle in a log potential, because up to now in the flat potentials, the alpha was always half. So for me, it's already boring, maybe also for you, I don't know, it's very late in the conference. So the log potential is also well known and well investigated. So what I think about is a charge wire. It can be very long DNA in principle. Of course, real DNA is finite, but let's say it's infinite. And I have a particle, this is the red particle, and it is at some distance with this long wire. And it's well known from electrostatics that this wire will give you a log potential. Log potentials have been investigated. We also heard here in the context of vortices. It's well-known example of a long-range interacting system. Of course, here I have only one particle. Now, if this wire has a finite size, there is a small-scale cutoff, because actually the pure log potential is problematic at small x and large x. So people always put in some cutoff to get rid of the problems. I like the problems. We will get rid of the small x problem. We will look at the potential 1 plus x squared. So the problem comes for large x. Why is it so? If I take this potential, I plug it into the Boltzmann equilibrium, it's very easy. It's exponential of a log. This gives you a power law. And the power law is x squared, this x squared, a large distance is minus 1 over 2 times the temperature. So if the temperature is less than 1, then this distribution is not normalized. You cannot normalize something that decays like a power law, like x to the minus, let's say, half at large x. It's not normalizable. So what happens? For low temperatures, the field is strong enough to bind the particle. This is in physics is called Manning condensation. You go to low temperatures and you see all the charges coming close to the wire and they condensate there. If you go to high temperature, it's well known, the particles will escape. And now what we are doing is we're just saying that while it's true that they will in some sense escape, but we can quantify the behavior of this particle slightly more precisely. And the transition point, this is because I chose here this coefficient as 1 over 2, the transition point is a temperature equal 1. So here, by changing temperature, you can go from ergodic normalized state to non-normalized state. Low temperatures binding and a perfectly normalizable Boltzmann give. High temperature, you go into a state where you have no normalization. So if I look, for example, it's very easy to do. I look at the potential. I look at the entropy of this particle. What I mean by entropy is P log P integration over x. I do it in equilibrium at temperature T. So this is already the long time limit. And I work in the Boltzmann phase. That is the low temperature phase. Then what you will see, you plug in the equation, you do the integration. It's not difficult. And you will see that this usual entropy blows up at temperature equal 1. So the blow up of the entropy indicates that something is going on here, and this temperature is the transition point from normalized to non-normalized Boltzmann-Gibbs states. So what does it mean that it blows up? In reality, if you start with some packet of particles, you know, the entropy cannot be infinity, it would be a finite time effect. So what will happen if you measure for finite time effect, you'll have here a plateau and it will go like log of t. Exactly like I showed you before, the long time limit, like in a free particle, the coefficients will be different, but here I have log of t, and of course, when t goes to infinity, all this regime, the entropy as if the equilibrium entropy, quote unquote, is as if it is non-normalized. Now, the log potential If the force field at large distance is 1 over distance, and it is pulling you back. And for this reason, you can show that the distribution of first passage times in this regime is such that alpha is 1 over half plus 1 over temperature in these units. And this is because, again, you come back, but you come back slightly faster than a free particle. So free particle is half, and when you add this force, which is attracting, 1 over temperature. So this transition, on the one hand, is a transition of the entropy from a finite value to an infinite value, but it's also a transition of the first passage time from a finite value to the mean first passage time. The mean return time is infinite here. And once you have these transitions, you get here, in this phase, you get the non-ergodic phase. And for example, but we worked on this extensively. We looked at the distributions, all these things. But for example, we have here some observable. This is the occupation time in some domain. We take the time average, we ensemble average. We know how to calculate the ensemble average. Again, when you have no normalization of the Boltzmann-Gibbs. And as I said before, this quantity, oh, here there is a bar missing. So infinite ergodic theory says that when you take this thing, you expect to get 1 over alpha. So this is a strange way. You take the time averages, and you get out of it the exponent of first return time. And of course, because in this example, this alpha depends on temperature, I can change the temperature in my simulation, and then I can get different results, and then we can simulate it, and you will see very nice convergence to this 1 over alpha. So before, the convergence was to this 2, because the first passage time exponent was half, and now it's some function that is very easy but depends on temperature, and you see that everything converges nicely for the asymptotically log potential. So just to summarize, we have, in my opinion, at least for single particles, we have binding potential fields. Here everything is very clear. You get to a normalized Boltzmann-Gibbs states when you have some dynamics inside here coupled to a heat bath. Then you have these log potentials. The force at large x is weak, and then you have these flat potentials. Of course, you can have other things, up here something, down here something. You could have also a sine function. I don't know exactly what happens, but if you have a potential which is sine, if you look at the central part, you will see something like a Gaussian, but you will see the oscillations of equilibrium of Boltzmann. It will be very similar. Then you have this potential, which is unstable. And then actually this potential with x to the power 3, this is really unstable. In the Fokker-Planck language, you reach infinity at finite amount of time. So here actually Fokker-Planck and the overdamped approximation breaks down. But actually also this case was investigated in some experiment and also theory, and in this archive paper. And what they showed is that if you look, let's say you have some kind of dynamics here. If you look at the rare events where the particle goes to this size, here you will see some Boltzmann distribution. So it's kind of natural, I think, but it's not that Boltzmann is totally wiped out. Of course, the number of particles in the rare events is going to decline very quickly. But if you have fluctuation dissipation in some region, even in this potential, you can see Boltzmann-Gibbs. It should be on the rare tails, according to this archive, which has also some experiments. So I just wanted to mention. I'll just briefly mention, maybe without going into too much details, that we can extend the virial theorem. So the virial theorem is usually, for x fx in this is the force. Then, for example, if this is harmonic, this is equipartition. What happens here is that these observables, let's say for flat potentials, are such that they are integrable, but you need to do some trick, some integration by parts. The bottom line is that with the non-normalized density, I can find this this virial theorem rather generally, and it depends on the virial coefficient. You need to get 1 minus the non-normalized states, And then you get this ratio. It decays with time because the particles are escaping. So if fx is going to 0 far away, so the particles are sampling far and far distances where the force is 0. So it's natural that it decays with time, and for example, like t to the half, if you have a free coefficient. And this is an example of the virial theorem, another example of this, this potential where I started with, and it's flat here, and then you have this infinite density, but then I can calculate the averages with this non-normalized distribution. It has a structure. And we also did a little bit on higher dimensions. This is an example. This is a potential field in 2 dimensions. It's rather simple. It's symmetric. You have this kind of Mexican hat which is flattened down. So here is the minima, and then you look at the coordinate r. So it's quasi one-dimensional, but still, the point here is that even though the return times are very long, we could find this type of infinite density for this system, but this is just simulation, and we can prove this also, but there's still a lot of work to be done on higher dimensions. I'll just leave it here. We just showed that, that if you have some stochastic dynamics, like Langevin dynamics in a force field, if the potential field is not normalizing, you can still construct some kind of tools which are taken both from thermodynamics and statistical physics, but the basics comes from infinite ergodic theory. And again, this was published with my student Erez Agion, who's moving now to Max Planck in Dresden, and with David Kessler. And I would like to thank you. I don't know if I have, I don't have references, but that's it.